This is the YouTube link for the live streaming session. Okay.
Is it recording?
Sorry for the delay. Welcome to the session. So this session is really for a quick revision and see.
Yeah, Utkarsh, can you mute yourself? Yeah, sorry. I think another session is also going on. Yeah. Okay. So
is it recording now? Is it?
Yeah, I've started the recording because I've also started the live stream, but in between it is stopped.
Okay, sir, can you just show that slide again where you would put the order of complexity, because I don't think that would have got recorded.
Okay, so first one. Yeah, this is the first one.
No, you just.
Okay, yeah. This one?
No, sir. You had shown that for
okay, slide. Okay.
Yeah, the slide, right? Yes, sir. That's it. Thank you.
Yeah. Okay. So you can remember these complexity in increasing order for your future purpose. You can also remember this. This is important thing. Okay. So now I'm moving to the next question. Yeah, I have received the response for this. So most of the answer is order of n square. So yeah, that is the correct answer. So you can see here we are using two nested loop here. So one is the outer loop for I in range n, and there is another loop which is running inside the outer one. So j in range n. So we can say that for every value of I, we are running n times. So there are I first loop will run n times, so n into n square time it will run. So we can consider the complexity of whole code is or big O n square. Yeah, this one is okay. Now next is this one, third.
Sir, the previous question, in what format we need to answer? Like
complexity is generally we are representing with big O notation.
No, like for example, if we need to type it in, so we can write it.
No, in quiz exam we generally not ask for typing the complexity.
Okay, thank you.
Okay, we will provide the option for that. Okay, so here this is the second code. So you can see that here we are running the outer loop for I in range n. So it will start from the 0 to n minus 1. It will finish, and the second loop is depend on the first loop I value. Okay, so it is starting from the I value and then running till n minus 1. Okay, so what the equation will be generated for this, and then based on that, what will be the complexity of this code. So just think about that. In the first time when I equal to 0, so how many number of times the second loop will run? So the second loop will also run from 0 to n. Okay, so that means the line number 4 will be executed n times for the first value of I. Second times, you can see that when I equal to 1, then second loop will be start from the 1. So that means the line number 4 will be execute n minus 1 times. And next time when I become 2, then second loop will start from the 2 and 2 to n minus 1. So that means we can say that the line number 4 will be executed n minus 2 times. So we will get one series and we can add all the steps. So after that we will get the complexity. So for the response for this is order big O n square n square n square n square. Okay, fine. And factorial. Oh, how we are getting this in factorial? n factorial n to the power q a. Yeah, these are steps n factorial. So those who are representing the complexity with n factorial, can anyone explain that? How you are getting this? How you are getting this n factorial? So this is a code, and so here you can see that in the for first value of I, the second loop will run complete n times. So we can say that the first value of I, we will run n time. For second value of I, our second loop will run n minus 1 time, and next n minus 2, so n minus 3. In that way we will move to the 1 point. Okay, 1. So here we can add the steps, we cannot multiply. Okay, factorial means you are multiplying the steps, n into n minus 1 into n minus n into n minus 1 into n minus 2, in that way. But we cannot multiply, otherwise it will be very high. Okay, so we can add all these steps to compute the total number of steps for this code. So in that way we will get this n into n plus 1 divided by 2. So when after computing this, we will get n square, the highest order of n. So complexity will be big O n square. Okay, so answer for this code is order of n square. The next one is this one. Okay. So those who have not joined till now this peer deck session, so just you can open the joinpd.com and just put this code, which is you can see in the top right corner, HLPVVZ. You just put this code and you can join this.
So what is n here?
N can be anything, and
Any
so
number.
here we are just considering this is input.
Okay, okay.
So we are representing a complexity in the terms of n, input n.
Yeah, understood, sir. I just got a little confused.
Okay. Yeah. Yeah, I've received 23 response out of 39. Okay, so let's try it. So in this code, we are just starting from the line number 1. So we are initializing I equal to 1, and there is one more variable we are initializing s equal to 0. But inside the loop, so loop condition is, so we will run this code until when I is less than n. Okay, so we will run according to this condition. So every time we are increasing this I by 2 into I. So for example, if we are starting from 1, then what will be the second value?
2.
So I equal to 2 into 1. So that means I equal to 2. Okay. In the next iteration, what will be the value? So 2 into 2, 4. Okay. In the next iteration, it will be 4 into 2, 8. In that way, so I value will be increases. So here you can see the pattern. So how we are increasing now. So for this code, I'm just seeing the response first. So I have received only 29 this time. Yeah, someone is trying to speak. Yeah, response. Log n. Okay, so log n. Yes, someone have written n. Okay, n by 2. Okay, n. So there are many options we have received order of n here. N. Okay, so most of them are log n, but many are big O n also.
Sorry,
Okay.
sir, I just joined. Where do I type in the answers?
You have to join this PDX session. So you have to open this website joinpd.com, and after that you have. Okay, I'm sending the link in chat box again. You can click on that. Okay, you have sent. Okay, you can just click on the link which sent by someone. Okay, now you can join. Okay, Vasu.
Thank you, got it, thank you.
Okay, yeah. So, okay, now the confusion. So many of have confusion for that. So, okay, how we can solve this? So here you can see. So our I value is increasing in that way. So first equal to I equal to 1. Okay. In the first iteration, it will become 2. Then in the next iteration, it will become 4. Then 8. Then 8 into 2, 16. And 16 into 2, 32. Okay. So if we are giving any n value here, so for example, if we are giving 64, n equal to 64. So how many number of steps you will reach this till this value?
6 steps.
Okay. Yes, 6 steps. So here first step is there. So then 2, 4, 8, 16, 32. And next iteration we will get the 64 value. So that means this loop will break at that point. So that means 64, when I will become 64, so this condition is not true at that time. So we will stop that. Okay, so you can see that this 6 is representing a log n terms. Okay, so we can see that this n equal to log. So generally we use the base 2. So this is a 64. Okay, so this is 2 to the power 6, and we can represent as a 6. N equal to, so total number of steps. Okay, k equal to 6. The total complexity will be log n for that.
Sir, could you explain again, sir, this one?
Yeah. So here you can see we are starting from the I equal to 1. Okay. When we are entering in this loop while, okay, here one condition is given. When I is less than n, then we will perform this loop. At any time when this condition become false, we will stop that. Okay, so every time when we are entering in this loop, we are increasing I by 2 into I. Okay, so if we are starting I equal to 1, in the first iteration it will become 2 into I. So 2 into 1 is 2. Okay, in the next iteration, for example, if we have set n equal to 64. Okay, so in the first iteration, after in the second iteration, it will be satisfied 2 is less than 64. Okay, it is true. Then we will enter again. Then the next time, what will be the value for I? 2 into 2. So it will become 4 here. So same time, so 4 is less than 64, condition is 2, then we will enter again. Then next value for I will be 2 into 4, this so 8. So we are increasing in that way. So 1, 2, then multiply by 2, then 4, then 8, then 8 into 2, 16, then 32, then 64. When we are reaching at 64, so this condition will become false. 64 is not less than 64. So our loop will break. Okay. So for n equal to 64, our total number of steps required are these 6 steps basically. Okay. So 1, 2, 3, 4, 5, 6. So here actually, so this total number of steps 6 is representing by this log n terms. Okay. So log 64 is equal to 6.
Thank you.
Okay. Okay, so the next one is, yeah, this for factorial. So here it is a recurrence, based on the recurrence. So just type the recurrence relation for that also. Okay, so with complexity, first type the recurrence relation and then type the complexity for that.
Sir, in the previous question, I less than n, if we do I divide by s, still it will be same crime complexity, right?
So in that way, we have to start from the larger value. Otherwise, it will run infinite time.
S we can initialize to 1.
So this loop is not depend on s.
So
So what you are saying again? Can you pardon? Can you repeat?
in the while, if we do I divide by s,
I divide by s. Okay. I equal to I divide by s. Oh, okay. So s is increasing by. So okay, in that way we have to check what we are getting. So for I equal to 1.
Atul, you keep the peer desk into the fifth question and work out in this.
Okay.
Right
Yeah.
section.
Oh,
Okay. Otherwise, we cannot answer that. That is for that.
okay.
Yeah.
Okay. So I'm moving to this here now.
Yeah.
So what you are saying? So you are saying that if we convert this line I equal to I divided by s. Okay.
in the while,
Inside the while.
yeah, just it's I by s. Yes, right.
Okay.
So it will show zero division error, no? Like right now it is 0.
The first iteration it will become, yeah, it will give error. So for example, if we convert this by 1,
Yes.
then
S we initialize as 1.
so 1 in the first, for example, we are putting n equal to, okay, we are taking the small example now, 16. Okay, so s is increasing by I every time. So Yeah, it will increase by, so it will become 2. And so are you still want to this line?
Sorry.
So line number 5, do you
Yes.
want? Okay, so
Same code, only the change in the while.
okay, okay. So then I equal to, we are not changing the value. Okay, I equal to 1, and then I equal to, it will become 2. So in the next iteration, once again it will remain the 1, 2 by 2.
Sir, I guess the time will remain same, but only if we check out for the individual, then there will be difference, but it will be log n, I guess.
Okay, I'm just running through it. So in the second iteration, it will be 2 by 2. Okay, so that will once again. Okay, now in the next time, so we will add s equal to 2 plus 2. Okay, that 2 by 2 equal to 4. So every time we are getting, I think, the 1 value. So 2 into 2, it will become 4. So 4 by 4, 4 divided by 4 will remain 1. 1 is less than 16. Now it will become 4 plus 4, 8. It will also become 8. So I think code will run infinite time for this condition, because we are getting I divided by s every time. So in the each iteration, we are getting 1 value here.
Oh, right.
Okay, Bikram?
Yes, okay.
Yeah, we are getting 1 value inside the while loop. 1 is less than n. So it will run infinite times.
It would have been different if instead of adding s plus I, we would be incrementing it by 1. Then it would be different now.
So you are just changing that s equal to s plus I.
No, instead of s plus I, s plus 1.
S plus 1. Yes, in that way, it will be different.
Hmm.
Okay. So, yeah, for this response. So I have received 33 for that. So here, recurrence, relation, and complexity. Okay. So factorial n. Oh, okay. So I think it is also not clear. So order big O n, yeah, that is fine. N is square t n minus 1 plus big O 1 n. Okay. It is also not correct. T n minus 1 plus 1. Yeah, it is correct. Complexity is big O n. N square. Okay. So n t1. Okay, big O n. N square. Yeah, so multiple type of answer I've received this time. So how we can solve this problem? So here one recursive function is given for factorial, and every time we are calling this factorial function with the input of n minus 1. Okay, if we are, for example, if we are starting from n equal to 5, then we will call by this factorial n minus 1, 5 minus 1, 4. And then the next next recursive call, we will call factorial 4 minus 1, 3, in that way. So here, what will be the recurrence relation for that? So recurrence relation will be for this function. So initially, what is the total time? Tn. And when we are running this, so we are calling the same function again with input n minus 1, Tn minus 1. Okay. Apart from that, what the function is taking time. So if you see, you can see that. So what the total number of operations? So every time we will check this if condition. Okay, so this is a constant operation, and at that when the our recursive function will return any value, so we will multiply this value by a so this n value. So this is also a constant operation. So we can see that. So apart from recursive call, we are performing a constant operation. So here we can write in that way. So we can simply write 1, or we can also write t n minus 1 plus, we can represent as a complexity big O 1. Okay, so this is a recurrence relation for that. Tn equal to tn minus 1 plus we go 1, yeah, or we can simply write 1. So after that, what will be the complexity for this recurrence relation will be? So every time, every time when we are calling recursively. So for example, if we are starting from Tn, okay, it is taking 1 steps, and we are calling again. This is so n minus 1, and so same things. It will take constant time. So for example, we are calling the same problem with n minus 1 input. It will take extra big O1 time for constant operation. So that means this is also a 1. Same things t n minus 2. It will take constant 1 time. So in that way, we will reach t1. So this is a base condition. When we will stop, it will also take a constant time. So you can see that so how many number of steps require? So in n steps, we will reach at the base condition. So every time we are taking one steps, one complexity. So if we will add all these, so this will be a n. Okay, if 1 plus 1 plus dot 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 1 n times, so we will get the n. Total number of steps require n. So we can represent the complexity big O n for that.
Atul, if you see the recursive process, now after reaching the base condition, it has to rewind back, right?
Yeah, that also will take the constant time.
Yeah, that is why I answered it n square because of that, because it will be like it has to go back, no?
Yeah, it will go back, but it will also take a constant operation. Okay, I'm representing the.
Oh, it will be 2n. Is it so?
N into, okay, so I'm just representing how it will work. Okay, 1 second. So for example, if we are starting
it will reach 1. Okay, it will reach 1. Then then it will wind back to 2. Then 1 into 2. Then wind back to 3. 1 into 2 into 3. Like that, it winds back up to n. Right?
Yes. So for example, if you are starting from T5, okay, so we will multiply inside that. So 5 into T4. Okay,
Yes.
same things we will. That means we will multiply by T. Sorry. So okay,
No,
T3.
5 into T4. Then
we will multiply
T3, T4, T2. Yeah. T1. It will become.
Okay, T1. This
Yeah.
is the base condition. Okay,
Right.
and we will return.
It will wind back again. It will go, because it has to reach base and then it will wind back.
Yes.
That is how recursive works, no?
Yeah, how recursive. Okay, yeah, you're correct. But here, what we are doing this is the last call, and we are returning a 1 value here.
Yeah.
Okay, so we are returning 1 here. So here we are getting 2. Okay, so I'm just represented wrong.
That one will go to T4. That one will go to T2.
Then 4 into T3. Then 3 into T2, and then 2 into T1, and then it will return 1 directly from here. Okay, so this T1 will return 1. So this is a constant operation. This is also a constant operation. So if you add all the steps, so you will get the 2 into n steps.
Yeah, 2n.
You can see that.
Yeah, so 2n, that makes sense. So
yeah. Okay, so in that way, this is also a constant operation. 2 into 1, 2, then 2 into 3, 6, then 3 into 4, 12, and then 12 into 5, 60. I think it is correct.
So the answer has to be 2n or n?
N. Complexity we generally represent with order of n. Okay, we will remove. Yeah, we will avoid the constant terms. Okay, so complexity will be big O n, and the recurrence relation I have explained that.
Okay.
Yeah, so this will be the where it is. Yeah, this is the recurrence relation for that. Tn equal to Tn minus 1 plus 1. Okay. So next is this one. So this is also a recursive function, but here we are calling 2 times. Ayush, you can join the peer deck and you can respond in the peer deck. So this is link. You can just click on that. I pasted in the chat box. Okay, I've received 33 response. So those who are not responding, please respond. Okay. So what is the answer? So 2t(n minus 1 plus 1) and complexity is n. Okay. Okay, so this is 2t(n minus 1 plus 2). Okay. But complexity is big O n. Big O n minus 1. Complexity is to the power n. Okay. Students to the power n. Okay, n. So okay, so this time I have received the recurrence relation is correct. Most of the answer is correct, but complexity is not looking correct in the most of the answer. Okay, so let's discuss. Okay, so so here we are calling this function 2 times. Okay, so we can represent the recurrence relation in that case. So Tn, this is the main time, and inside this we are calling the same function 2 times. So we can just represent that 2 into Tn minus 1. Okay, that means we are calling the same function 2 times with the input n minus 1. Okay, so in both way the input is n minus 1, and apart from that we are performing some checking operations. So this is a constant operation, and after that after getting the return value from both function, we are simply adding these value. So this is also a constant operation. So we can see that we are performing constant operation. So we can write in that way 1, or we can also represent by big O of 1. Okay, so this is a recurrence relation for that. But what will be the complexity? Okay, so for example, if we are starting from Tn, okay, so it is taking a constant time 1, but in the next step, so our we are calling the same function 2 times to t n minus 1 and t n minus 1. Okay, so this problem will also take one time, it will also take one time, so we can just represent this by 2. Okay, 1 plus 1 2. Same once again, this problem will again call recursively 2 times, so t n minus 2 t n minus 2. Same for this problem, t n minus 2 and t n minus 2. So this is taking 1, this is taking 1, this is taking 1, and this is taking 1. We can represent 4. Okay, same way it will divide like this. So 1 1 1 1 1 1 and 1 1. So it will take 8. So you can see the pattern. So 1, this is 2 to the power 1. So here we can represent 2 to the power 0, and this is 2 to the power 2. This is 2 to the power 3. Okay, so total number of steps required at this level is 2 to the power 3. So this is the third level, and when we move to the nth level, because we are reducing the value of n by 1 every time. Okay, so in nth level we will reach at the t1 base condition. So this is a 0, sorry, t0. Okay, so at that time, what will be the value of here? So it will be 2 to the power n. Okay, so this is the highest. If we will add this 2 to the power n plus 2 to the power n minus 1 in that way, so this is the highest order of complexity. So we can pick up this 2 to the power n. Okay, so complexity will be, we go 2 to the power n here.
Sir, can you just explain why it is 2 to the at the beginning, sir, Tn is equal to that, at the end it's plus 1. Why is it plus 1?
Which one? Where?
So Tn equals 2Tn minus 1 plus
Okay,
1.
so this plus 1. Yeah, this
Yes.
plus 1 is basically a time which is required by this function, apart from the recursive call. Okay, so here we are calling recursively, here we are calling recursively, but apart from that, what the function time is, what function taking the time. Okay, so here
So how
this
do
is
we
a
know it's
cost,
1?
because you can simply check the code. So this part is just simply a checking things. We are just checking this n equal to 1. So this is a one constant operation. Okay, and
And
when we will,
equals to 0, sir.
yeah, so this is checking operation. Here we are just comparing the two value.
Okay.
Okay, so this is a
Okay,
constant
so
operation.
that's why we are taking it as a 1.
Yeah, 1. And there is one another operation. We will perform this operation when we will get the return of the function. Okay, so this we will return anytime we will return any value from this function and this function also. So we will simply add this. Okay, so this addition will also take a constant time.
Okay, sir.
Okay, so because of that we can return here 1.
Okay.
So this is the recurrence relation for that, and complexity will be big O 2 to the power n. Okay, we'll move to the next one. Yeah, so now we are starting from the sorting algorithms. So here one code is given. So you have remembering this code. This is a simply selection sort code. You are looking at in the lecture code. So just check this, for which input, for which of the following input list the return output list would not be stable. So you know that what is the definition of stable? Here definition is also given. So after sorting, the output list is stable if R appears before S in the sorted output list. Whenever there are two elements R and S with the same value, and R appears before S in the input list also. Okay. So in simple meanings, order of the similar element in the input list should not be changed in the output list. So this is called the stable. So for which input this selection sort algorithm will not return the stable output. So you can see that in every input, so two or more similar value are given. So here I think only two similar value are given. Just check that these two value are coming in the same order in the output list or not. So 4 4 4 4, yeah, 4 4 is repeating in every list. Okay, so I've received 26. Oh, and this at least okay. So now the multiple answers there. So D have 7, 12 is C. Okay. So now B have 3 and A is 5. Okay, so I think it is also not clear by everyone. Okay, so how we can check this? So simply, if you know the concept of selection sort, so I think
Sir, 1 second. This is MCQ or
MCQ,
MCQ, not MSQ. Okay, got it. It's C.
Yeah, it is MCQ.
Okay, got it. Sorry.
Okay, so if you know the concept of selection sort, you can directly check without checking the code. Okay, so here we can check L equal to 3 1 4 2 4. Okay, so this is the first list. So you know that in the selection sort we start from the first node and we just check that which one is the minimum in the first iteration. So you can see, or so in this list only two value have similar, so this one and this one. We will focus on that. So if the order of these value are changing in the output, then we can see that this is not stable. So in the first iteration, you can see that what is the smaller value? This is 1. Okay, and this 1 will be replaced by the first value. So we will represent by 1, 3, 4, 2, 4. So order is not changed. Okay, now in the second iteration, so okay, we will cut this. We will not check this one again. So in the second iteration, we will check what is the minimum value. This will be 2, and this 2 will be replaced by this second one. Okay, so 1, 2, and 4, 3, 4. So in these steps, we are also not changing the order of 4. Now in the next steps, what is the minimum value is 3. Okay, and we will replace by this 4. So after swapping this one, so we are getting 1, 2, 3, 4, and 4. Still, you can see that we are just swapping this 4 by 3. So here we are also not changing the order of 4. Okay, so in the next step, the value is not small. So initially we can consider that the first value is smaller. Then we will compare that. Okay, so here this is a 4, and we are not getting any smaller value compared to this one. So we will not swap anything after that. So here you can see that in this for this input, so order is not changing. Okay, so we will move to the second input. So same 4, 4, 3, 1, 2. So here you can see that so we are performing the first iteration. So we will just get that this value. So 1 will be swapped by the first 4. Okay, so 1, 4, 3, 1, 2. Oh, sorry, not 2, 4, 2. Yeah. So here you can see that the order is changed of the 4. Now once again, when we just compare that by in the next iteration, so what will be the next smaller value? 2, and this 2 will be swapped by 4. So that means it will come here. So that means it will come in the same order of the input order. Okay, so 1, 2, 3, and then this one is 4, and this is come here. So 4. Okay, so now order is corrected now as input. But in this first iteration, the order become wrong, but in the next iteration, it will corrected now. Okay, in the next iteration, now 3 is the smaller than, it will not swap. Then after that, it will not swap. So that means in the output list, the order is remain same as input. So this is also correct. In the next iteration, 4, 4, 3, 2, 1. So we will swap this by this one. So order is changed. So 1, 4, 3, 2, 4. Okay, now order is changed here. I'll just mark this. Now in the next iteration, we will swap this. Okay. So 1, 2, 3, 4, 4. Still order is changed compared to the input list. After that, the list is sorted order. So we will not perform any swap operation after that. Okay, so that means in the output list, we are getting incorrect order compared to the input. So that means for option C, so this is MCQ. So after getting the correct answer, we will not required to check the next. So C is the correct answer for that. Okay. Oh, so you can read these properties. So I think some things is given. Which algorithm is stable, which is not stable. So this is also important. So here you can remember these some parameters and value for each algorithms: selection sort, insertion sort, merge sort, and quick sort, which we have learned in the course. So what is the complexity for in each case? Best case, average case, worst case, in place or so algorithm is in place or not, stable is not. Okay, so selection sort is not stable, insertion sort is stable, merge sort is stable, and quick sort is not stable. So you can learn or you can remember these basic things about the sorting algorithms. Okay, so C is the correct answer for that. Now move to the next one. Yeah, this is based on the insertion sort. So for complexity of the selection sort, so selection sort complexity will remain same in each case. Okay, so if you provide any type of input, if you provide the sorted order in input list, it will remain the big O n square. Okay, so the code is not dependent on the input order, so it will perform completely, and the complexity will remain the same order of n square in each type of input. So now this is a insertion sort. So for input L equal to this list, how many number of times we will perform swapping operation? Means line number 8 will be performed. So in simple terms, we are asking the swapping operation. How many times we are performing swapping operation? Yes, Susma Kumari, can you join from your IITM email ID? Yes, Susma, am I audible? Okay, so now I've received very few response for that question. Okay. So I'm opening the answer. 6, 2, 6, 6, 7, 6, 36. Okay. 7, 1, 6, 2, 7, 6, 7, 4, 6. It is 3. So most of the answer are 6, but still there are many another answer are also there. So for this list, if you know the concept of insertion sort, so what we generally do with the concept insertion sort, we just shifted the element and put into a correct position. Okay, so for example, if we are starting from this input list 3, 2, so for the first element, okay, 3, 2 in the first iteration, 4, 1, 6. So we will generally consider that this is a sorted. Okay, we are just starting from the first element, so single element is generally considered as a sorted element. When we are checking for the second element, okay, so we will compare this element and we are considering that the previous all elements are in sorted order. So we will just compare the next element by a just previous element of this one. Okay, so we will compare this 2 by 3. So if it is not in the correct order, then we will perform the swap operation with this. Okay, then we will perform the same things with the next element at any time if the order is correct. So we will stop that. So here you can see that 2 3, when we are just checking for this 2, so this should be come before this 3. So that means this 2 is not at the correct position. So we will perform one swap operation here. So 2 3 5 4 1 6. Okay, so now count is 1. Now this part is sorted. Okay, now we will check this 5, and we will just compare this 5 by the last element of the sorted part. Okay, so we will compare this one 5 and 3. If it is sorted, if it is already sorted in the correct order, so we will not check the we will not compare the another elements with the another elements. Okay, so if this 5 should be come after this 3, that means it is in correct order. So we will not perform any checking operation after that, and then we will move to check the further element. Okay, so that means in this steps we are not performing swapping operation. That means 2 3 5. So now this part is already sorted. Now we will check the next one, 4. Okay, now we will compare this 4 by 5. Okay, so here we can see that this 4 is lesser than 5. So we will perform one swap operation here. So now 2 3 4 5 1 6. Okay, now the total number of swap operation is 2. We will check once again by this. We will compare this one. Now here you can see that this is in correct order. So we will stop that. Okay, now that means we will not perform any other swap operation. So now this part is sorted. 4 5. This is sorted order. Now we will check next part, 1. Okay, so now 1 is lesser than 5. So we will perform one swap operation here. So 2 3 4 1 5. Okay, now we will compare. So here 3. Now we will compare this 1 by 4. Okay, so this is also not in correct order. We will perform one more swap operation. 2 3 1 4 5. This is 4 now. Now we will compare by this. Okay, so this is also not in correct order. So we will perform one more. 3 4 5. Okay, so 6 is missing. Yeah, so one more 5. Now we will compare by this one. Okay, so this is also not in sorted order. So 1 2 3 4 5, and then 6. This is 6. Now total comparison is 6 here. Now this part is sorted. Now we will compare the next 6. So 6 is greater than 5. That means it is already in sorted order. So we will not perform any other swap operation. So 1 2 3 4 5 6. This is the output list. So now in this procedure we are performing 6 swapping operation. So this will be the answer.
Sir, in the exams too, will the code be provided or we have to remember it?
Yeah, code will be provided.
Provided, is it, sir? Okay. Because otherwise it gets a little cumbersome to do it, the looping.
Otherwise implementation can be different. So
Yeah.
because of that, we will provide the code.
Okay, sir.
If you find the same code which you have learned in the course, you can directly perform the concept. Okay, so now next one is, just remember this. This is a merge sort. You're asking for the merge sort. What will be the recurrence relation of merge sort in best and worst case? So about the insertion sort complexity, okay, you know that what will be the complexity in worst case of insertion sort?
N square.
N square. Okay, and what will be the complexity in best case?
N.
N.
Yeah. So what will be the type of input for N complexity?
A sorted list.
Okay, if it is already sorted, that insertion sort will take n times. Okay, so another question is also possible if all elements are same. Okay, if all elements are same, that it will also perform before n times by the insertion sort. Okay, now the next, this one is merge sort. What is the recurrence relation of merge sort in best and worst case? Six. What option are given? Best case 2t n by 2 plus 1, 2t n by 2 plus n, 2 plus n, 2t n plus n. Okay. So what are the option? Okay, this time also we are getting multiple. Okay, so 12 have marked A, 9 have marked B, and this is C. Okay, so if you remember this merge sort implementation, so merge sort is also not depend on the input. So the merge sort perform the full operation on the every type of input. So complexity, if you remember that, the complexity will remain the same n log n for each case, best, worst, and average. So the recurrence relation will also be remain same in each case. So what will be the recurrence relation? So here you can see that we are performing one merge operation in the merge sort, and apart from that, we are performing a dividing operation. So generally, we call this divide and conquer algorithms. So dividing part is basically a recursive part, and apart from that, we are performing a merge operation. It is taking order of n time. So here you can see in the option C. So that means we are dividing the problem into a two problem every time, two problems, yeah. And each time we are performing a merging operation, so it will take n times. So here option C, I think it is representing a correct recurrence relation in both cases. 2t n by 2 plus n, and yeah, this is the same. Yeah, so C is the correct answer for that. Okay.
This come back again. I just got confused.
Yeah, so if you remember the merge sort algorithm, so okay, I'm just opening this. Merge sort, quick sort, data structure. No, this one. So here merge sort is given. Yeah, this one. This implementation is given. So here you can see that this part. So this is a main part of the merge sort algorithm. So here this is the base condition, and apart from that, we are calling the same function two times. Okay. So this will create a 2t n by 2. Okay, we are just dividing a problem with the input half with the half input every time. So we can just represent the 2t
because both halves are getting independently sorted.
Yes, yes. We are performing sorting on the both part.
Right.
And apart from that, we are just merging the solution. So we are calling this merge function.
That will be plus n.
Yeah, so that will take the order of n times.
Right.
Okay, so because of that, the recurrence relation will be, so here recurrence relation, I think it is not given. Stable. Okay, so recurrence relation is not given. So final recurrence relation will be 2 t bracket inside the bracket n by 2 and then plus we can represent big O of n.
Okay, I got it. Even in merge sort, even if the both elements are completely in the sorted order, you have to still traverse.
Yes, we have to perform the all operation.
Right. I got it.
Okay. So now,
I have one doubt. So I actually guessed the option C, thinking that in merge sort all the cases are the same, right? Time complexity is n log n. So
yes.
can I take, even if it is not the merge sort, in the exam, if some other thing is given where the three cases time complexity is the same, so shall I go with the same guess that recurrence also will be the same?
No, you have to check the code, how we are performing this.
So we cannot consider just the time complexity because the time complexity is same for all the cases.
No, we are not getting the answer because of the complexity is same. Okay, we will just remember the concept of merge sort, and then based on that we will.
Okay, so even though the time complexity is same, it may differ in the recurrence. That's what you're saying.
Yeah, recurrence relation can be different. Yeah, it can be different.
For the burst and the best and the worst, that's what you're telling. It can
Not
differ.
In merge sort, recurrence will be same, no? Like
yeah,
No.
recurrence will be same.
My question is, merge sort we know, but if some other code is even the code without the code, if the time complexity is same for all the three cases, can I
So
say?
for example, if we talk about the binary search or ternary search. Okay, so in that way you will
correct, sir. It could be n by 3, n by 2, but eventually it will be log n.
Yeah, so complexity will remain log n, but the recurrence relation will be different.
Okay, thanks.
Okay. Yeah, so move to the next one. Yeah, this
excuse me, sir.
Yes, Rashti.
Sir, please share the YouTube link in the chat box.
So YouTube link is not working right now. Okay, so we are recording this session and then we will upload it later.
So on the portal?
Not in the calendar.
Okay, sir.
Okay, so after the session we will upload the recording on the calendar.
Okay, sir, no problem.
I think there is some technical issue in the Gmeet. So this question is based on the quick sort algorithm.
Sir, in the question there is 5 options, but for clicking it we are getting only A, B, C, D. We are not getting A option.
Oh, okay. So this is viewing as MCQ.
Yes, sir.
Okay. Right now I cannot
A and D are the answer. So we are not able to type in both.
Okay, just put the answer in chat box for that.
A and D. Okay.
A and D.
Just put your answer in chat box. Okay, so A and D is the answer. D, A and D. Okay. Okay, so fine, we will discuss this. Yeah, this one. Okay, so here you can see that just you can remember some things about the quick sort. What will be the recurrence for the quick sort in best case and worst case? Can anyone tell me?
N log n for the average and best case. Worst case will be the n square.
Worst case is n square and n log n is
Best
case.
and average case.
Okay, yeah, correct. And what will be the recurrence relation in in worst case and in the other case?
Like divide and conquer, it will follow. So for the best case, same as the merge sort.
Yeah, it will be 2 into Tn by 2 plus n.
Yeah,
And
correct.
for the worst case, it will be Tn is equal to Tn minus 1 plus n.
Tn minus 1 plus n. Yes, correct. Okay, yeah, correct one. And okay, so what will be the so here what is given? So in the first option, the best case is when the pivot element always divide the list into two equal halves. So this is the correct one. Okay, so we will get the best case situation for that. Second option is that the best case is only when the input list is arranged in ascending order. Okay, so it is also possible when the input list is descending order. No. So okay, so this is best case. Okay. Best case. Yeah. If our input list is in ascending order or descending order, so it will be a worst case for
Worst case.
Yeah. So this option is not correct. Option B. Option C, the worst case is when the pivot element always divide the list into two equal halves. So this is not a worst case. This is a best case condition. Option D, the worst case is when the input list is either arranged in ascending or descending order. So this is correct. And the last option is that the worst case is only when the input list is arranged in descending order. Okay, so this is only given in the descending order, but the worst case is also depend on the ascending order. So option A and D is correct. Other are not correct. Okay. So we are moving to the next one. Okay, we have discussed this one, so I am skipping this. What is the recurrence relation of quicksort in best and worst case? Okay, moving to the next one. Okay, so this question is based on the linked list and stack and queue. So now we have moved to the B3 concept.
Was there 11th question? Did I slip it?
No. We have discussed in the previous one. What is the recurrence relation of quicksort in best and worst case? Okay, we have discussed the answer.
I just missed it. Okay.
Because of that, I have skipped.
Okay.
So, will making a queue into a linked list will make different, or will it be acting like a queue?
No, we can implement queue using a list as well as we can implement also using a linked list.
Okay.
Okay, so queue. Okay, so appending, yeah, we can improve the complexity if we are implementing the queue using linked list. Okay, we will discuss about that in this discussion.
So in this question, are we defining head and tail self.head is equal to none and self.tail is equal to none?
So here it
Okay.
is given in the first statement. We
Right.
have one head pointer that is containing the reference of first element. We have also one tail pointer. It is containing the
Okay.
reference of last element.
Okay.
And apart from that, every node is containing the address of next element. Okay,
Right.
so
So we are only changing head and tail, right? Right, sir.
Yeah. So we can traverse the list, or we can update the element using this head and tail only. Okay, we can start the traversing from head if you want to update the middle element or anything. So here we are implementing the queue using this linked list. So what question is given? What will be the complexity of in-queue and D-queue? Yeah. Okay, now I've received 27 response. So I think many of are not responding it. So out of 45, only 27 have responded. Okay, let me do the answer. Option A, I've received 15. So B is 5, 4, and 4. Okay, so A should be the correct answer. Okay, just check that. So 1-1. Okay, so here we have so here what we are performing? We are performing in-queue operation from the first position. Okay, so no. Let in-queue will be implemented by inserting a new node at the tail. Okay, and D-queue we implemented by deletion of the node from the head. Okay, so we are inserting the new element at the last position, and we are removing the element from the first position. So what will be the time complexity for that? Okay, so if you have these two pointer head, which is containing the reference of first node, it is containing the reference of last node. So we can perform the insert operation at the last position in the constant time. So what we will require for that? So we have the reference of last node. So we will just create a new node, and we will update we can directly update the address of the last node next field. Okay, so for example, this is a next field. We will currently this is representing a null value. Okay, so we will simply update the address here. We will just save the address of new node here, and then we will put the null value here. Okay, null, and we just assign the tail equal to this element. So these three operations is required to perform the insert operation at the last position. Okay, so that will so we can consider this is a constant operation. Same things if we want to remove the first element from the list, so we can directly perform that. So we can simply assign this head pointer. We can copy the address of second element by in this field by the first element next field. We can copy the address of the second element from here, and then we can directly assign to the head. Okay, so we will directly read the address of second element from this node, this position, and we will directly assign to the head. So that means we can directly assign the head, and we can remove this. So this is also a constant operation. So that means we can perform both operation in a constant times. Okay,
sir, I have a doubt on
to go to the tail. Shouldn't be, I know there's a pointer referencing to the last node, but don't you have to traverse the whole link?
No. We have already the reference of last node, and we want to insert them. We want to performing a insert new node operation.
Since it's been mentioned that it is NQ and DQ, so that's why we have the pointers pointing this first and the last. No. Is it like
Yeah,
that?
so this is a question. Actually, it is given, some implementation is given, and according
So
based on that.
basically, had the tail not been given, then probably it has to traverse to the entire
Then
tail.
we have to traverse. So I'm coming on that. So for example, if we have a list, so one is head. We will discuss the all case now. So this type list if we have, okay, and this is a last element. Okay, so now I want to perform insert operation at the last position and delete operation from the first position. So now what will be the complexity of insert operation at the last position?
N.
Will be n.
Okay, so we are just considering we have n element in the list. Okay, so yes, so for insert a new element after the last element, we have to traverse the list from the starting node. because we cannot directly find the address of last node. Okay, so we will start the address from the first node because we have only head for the linked list. So we will traverse the whole list, and then we will at the time when we will reach at the last element, then we can add the new element at this position. Okay, so it will take order of n times, but we can remove the first element in a constant operation. Okay, so this is now okay. So now in the second case, if I want to remove the last element, what will be the complexity? Okay, so for the same previous implementation, just consider the previous implement. If I want to remove the last element, what will be the complexity?
N, order of n.
Because it has to transverse for the whole thing.
Yeah. So if I want to remove last element, so in that case, we have to set null value in the previous element.
N minus 1, right?
Okay, so we have to set null value here, and we cannot directly access the address of second last element because our node is containing only the next address, not the previous address. And so this is the one step we need to set after removing the last element. And the second step, we have to set this tail equal to this second last. Okay, so before that, so we have to find out the second last element. So we have to traverse the list from the starting node. So in that case, we have to traverse n minus 1 elements. So we can simply write the complexities order of n10. Okay, so if the implementation is different, for example, I think you know that the doubly linked list structure. So like that in doubly linked list structure, it is given in that way. Here, every node contains the address of first previous element and next element. Okay, this is a tail. So this is null, and this is null, and this is head. Okay, head is containing a address of first element, and tail is containing a address of last element. So in that case, if I want to remove the last element, what will be the complexity?
Order of 1.
Order of 1. Now we can remove this last element in constant operation because we can read the address of the second last element from this position. Okay, so this position contains a previous address, and this position contains an address of next elements. So we can directly read the address of this position for the second last element, and then we can directly move to here. We can directly assign tail equal to this position, and after that we can simply assign null value here.
So will a doubly linked list always have a tail?
No, so generally we contain this tail. Otherwise, it is depends on our implementation.
I think pointer is
We can
our decision. I need to have
our decision.
Pointer or not.
Yeah, for singly linked list, we can also take the tail. We can also ignore the tail if it is not required. Okay, so it depends on our decision. Okay, now in that way you can decide the complexity. How we can read the address of elements, and how many steps are required. You can decide the complexity for linked list. Okay. So this is the next one. This is based on the queue. So you know the concept of queue. We can insert the element from one side, and we can remove the element from another side. So first in, first out. This is the concept of queue. So just perform this operation sequentially, and then tell that what will be the removed element sequence. When we are performing DQ, so what will be the output? What will be the sequence of output? Okay. So now the answer is C. Okay. So now this time 22 is marked as C. Only 4 is marked as D. Okay, just check that. So you know that the concept of queue. In queue operation can be performed on from the one side, and DQ operation can be performed on the another side. So when we perform the DQ operation, it returns a deleted value. So for example, if we are performing a in queue operation, so 10 will be inserted at the first position. Then we are performing again in queue operation. So 20 will be inserted after the 10. So for example, if we are inserting from the last and we are for DQ, we will remove the first. So now we are performing one DQ operation. So we will get in output 10. Okay, now our queue have only 20. Now in queue 10 will look like this. Now once again 20, we will get look like this. So DQ, DQ, DQ. Okay, so we will get the sequence 20, then 10, then 20. Okay, first, second, third. In this order, it will be removed. Now after that, we are just performing one more in queue. So after removing all these, so our queue will become empty, and then we are performing inserting 20 and then DQ, so 20. So this should be the correct answer. So 10, 20, 10 and 20, 20. So this is the option C, 10, 20, 10, 20, 20. Okay, so now this is the correct one. Okay, so next one is also based on the same concept, but now this time we are taking a data structure stack. Okay, now 23 I have received. Now this time is B is the correct one. Okay. So we will simply perform the these two operation on a stack. So we can simply push 10. So for example, we are inserting element 10. The next element will be inserted on the top 20. And when we are removing the element, so we will perform the remove operation from the top elements. Okay, so in stack we can perform last in first out. Those elements are inserting in the last, it can be removed first. Okay, so here the now first pop operation we are performing here. So 20 will be removed. Now our stack will remain only 10. Now we are performing push operation to 10. So 10 and then 20. So now 20 at the top position. Now we are performing 3 pop. So 20 will remove first, then 10, then 10. Now stack will become empty here. Now we are performing one push operation 20 and then pop. Okay, so it will be 20. So 20, 20, 10, 10, 20. So 20, 20, 10, this is the D option. Okay, correct one. Okay. So now this question is based on the hashing. So here the definition, yeah, the definition of linear probing is given. You know the hashing concept. In hashing, we generally generate the index using a hash function, and in the same way, we can find the index using the same hash function. So generally, in the Python dictionary, use this hashing concept. So here you can find any element in a constant time. Okay, so there is one approach. In the hashing function, it is given in the question linear probing. So linear probing is an open addressing scheme in computer programming to resolve hash collision. Okay, so collision means if we are getting the same index for two or more value, so that is called the collision. And so how we can remove this collision to store the value? So generally we use this some techniques. So linear probing is one of them. So linear probing takes the original hash index and increment the value by 1 until a free slot is found. Okay, so I've received 21 response for this question. So just check that 4. Okay, so 446 is also coming. 443 So please explain selection sort question once more. Okay, I'll explain that. 2. Okay. So now this time we are getting 4 is the most answers. Sorry, we are incoming. Okay, how we can solve this? So here one linear probing is given. So in that way, so now the question is the hash table contains 10 buckets. Okay, so we are just creating a table which contains 10 buckets, and if the index is starting from 0, 1, 2, 3, 4, 5, 6, 7, 8. So one more is required. 9. Okay, so we have one sequence. Okay, so what is our hash function? So hash function is key mod 11. So we can simply write key k mod 11. Okay, so our sequence is this. Now first we will insert the 56 in our hash table. So we just put 56 here mod 11, and we find what is the remainder value. So it will be 1155, and this will be 1. Okay, so 56 will store at this position 56 because this is empty. Now 166. So 166, what will be the remainder of for this? So this is 1 and this 56 same 1. Okay, but 1 is already occupied by 56. So we will check the next position. So what will be the next position after that? 2. So 2 is empty. We will put this 166 here. Okay, this is the approach we are using in the linear probing. So next is 80. So 80, what will be the remainder? Will be 3. No, sorry, this is 80. Okay, so this is now the remainder will be 3. So 3 is empty. We will save this here. Now next is 16. 11 equal to, what will be the value? 5. Okay, 5 is already empty. So we'll put here 16. Now 145. So that is the person. At what index would the key value 145 be inserted? So 145 by 11. Okay, so this 1 and now 3, 3, 5, 32. Okay, so 2 is already occupied. Now we will check the next position. It is also occupied by 80. Now we will check the next position. It is empty, 4th index. Okay, so we will put here 145 here. So this is the correct answer for that. Okay. Yeah, now the question, we are moving to the B4 concept.
अतुल सर ये डेक आप शेयर करोगे ना?
स्लाइड्स या हाँ मैं शेयर कर दूंगा इसको,
क्योंकि मैं ना अभी कॉल में जा रहा हूँ तो आई विल बी देयर.
Yeah, okay.
I'll see it later.
Yeah, I'll share on the discourse.
Okay.
Or okay, I can also. Okay, I'll share on the discourse for it. Yeah. So this is the next one, based on the B4.
Sorry, I missed the last answer. What was the answer, sir?
4, 4.
4.
Yeah. So we will insert 145 at the 4th index. So now this is the B4 based question. Now this is the 16th and we have 25. So we have approx 10 question based on the B4.
Atul, I have one doubt regarding the previous question. So what if the list is like Anwar asked, if the list is bigger and there is no free slot, so automatically will it be extended, the memory, or?
No, that is actually, that's condition. So that situation come in very few cases. So generally,
so the hash table will always have an extra space compared to the list. Is that so?
it depends on the system structure, how it is providing the memory for the data structure. It depends on the data structure.
Okay.
So this type of situation never occur.
Okay. Yeah.
Okay, so this will be large.
This is DFS.
Yeah, this is DFS. Suppose we obtain the following DFS tree rooted at node G for an undirected graph with vertices. So these vertices are given. So which of the following cannot be an edge or edges in the original graph? Okay, some edges are given in the original graph. So just check that that edge are possible in original graph or not. Okay, so now 23 response I have received. Option B and D, B, D, C, B, D, B, A, D, O, D, B, C, D, F, D, F, D, C, B.
D, C, B, B and D.
F, D is B and C, B is D. Okay.
B and D.
B and D. Okay. C, D. So multiple option I'm getting.
Okay. So can you just show us how to draw these BFS and DFS trees?
Mm-hmm. So DFS tree, this is the way how we can traverse the graph. Okay. So this is one possible DFS tree which is generated by a traversal using the DFS algorithm for any graph. And after that, we can check that. Okay, so I'm just explaining that how we are getting the answer for that. So you know that in the DFS algorithm, we traverse the graph. So we just traverse the adjacent node, and we traverse the graph based on the depth. Okay, so we just traverse the adjacent and the adjacent of adjacent in that way. In DFS, depth first search. Okay.
Correct.
So we completed the one depth, and then we reverse back, and then we traverse the second depth. Okay. So in that way. So for example, this is the final traversal tree. So which we are traversing any graph, and we are getting this tree. So that means we are starting from G, and then we are traversing node, for example, K, and after that F. So after that, there is no node available which are connected. So we are reversing that on the K, and then we are moving to the another depth D. Okay, so in that way, this traversing is performing on any graph. So okay, so this traversing is performing on undirected graph. Okay, yeah, undirected graph. So now we will just check that what are the edge possible. Okay, so for example, if we connect, so just consider that this is the original graph. Okay, this is the original graph. If we are just traversing the same graph, we will get the same tree. So if you just consider that, where is this one? Yeah. So for example, this is the original graph. Okay, we are traversing this graph, we will get the same tree. Correct?
Yeah.
Yeah. So now just add these edges. Okay, so DG. So what is the DG? Where it is connecting DG. In that way. So for example, in the original graph, if this edge is connected, okay, just perform the DFS again. So what the answer are possible? So in that way, DG, we are performing DFS in. Okay,
DG
so can
will form a cycle, right? So it won't be in the DFS.
Okay, yeah. So so a question is asking for cannot. Okay, cannot be an edge. Okay. So for example, if this edge is connected. So and you are just traversing the graph. Okay, so you will get the same tree for this. So you will traverse the same G again, and then K, and now F is connected. So you will move to the F, and then you will reverse back to the K, and then just check that what is the next node is connected from the K, and then you will get the D. Okay, when so there is no node available after D, then you will move to the G, and at this place you are getting there is one another edge G to D. So but when you are considering this, but D have already traversed, so you will not traverse this tree, this edge again. So because it is creating a cycle, so you will move to the this part. So that means if this edge is connected, so you will get the same tree. So this is not affecting the output tree.
So DG is part of the original graph or not?
Yeah, it can be part of the original graph.
Yeah,
If
that's
yeah, it can be part of the original graph. But in the question we are asking which edge cannot be the part of original graph.
F and D cannot be.
Yeah. So this DG can be a part of original graph because it is not affecting the output tree. If we are connecting this, we will get the same traversal tree. Okay, but when we are taking this BFD, okay, I'm just removing this now.
Sir, I have a doubt. Actually, from G it went to K, and G it went to I also. If there is a edge from G to D, there will be another node from G to D direct, na? Yeah. Then in original it will not be there, right? G and D.
No. This is a output tree, output traversal tree, which is generating by a DFS algorithm. Okay, here we are asking that which edge is possible in the original graph which we are traversing. So if we are adding this GD, so you will get the same tree. Okay. Okay, so that means it can be a part of original graph. It is not affecting the output tree if we are connecting this.
Okay, right.
Okay, so for example, if we are taking the second edge now, so you can see that how the output tree will be affected. Okay, FD. So if we are connected this FD, okay, now just traverse again. So you will get the G first. Okay, so K. Now you will move to the next F. But at FD, if FD is connected, so you will move to the next D now. Okay, you will not back to the K. You can directly traverse this side. Now you will get this type of tree. Okay, so so after that you will get you will reverse that complete path and then you will move to the another part. So you will get this type of tree. H, B. It will remain the same. Right side will remain the same. So you can see if we are connecting this F and D, so our output tree is changing. That means it cannot be a part of original graph. If we are adding this, then our output tree will not remain the same like this. It will become changed.
So can you please repeat?
So for example, if we are adding this FD in a original graph, okay, and we are performing a DFS algorithm from node G. So what type of output T will be generated? Here you can see that we will start from G and one adjacent, if we are traversing K, then we will traverse the next adjacent of K. So this is F1, okay? And if F and D is also connect, so we will move to the F to D here. So that means this tree cannot be generated if we connect this F and D.
Yeah.
Okay, because of that, we cannot say that we can see that this FD cannot be a part of original graph. Otherwise, output tree will be different. Okay.
Can I suggest a simple trick?
Okay, yeah, sure.
See, any two vertices in different branches can't be part of the original graph. Right? Otherwise, they would be an extension because you would probe till the end. Right? So,
yeah, correct.
FD cannot be, CJ cannot be, EA cannot be, HB cannot be, CB cannot be, right? So, because if F and D were connected, then D would be under F because depth first, right? You'll keep going till the end. Only because your D is a separate branch, because from F you're coming back to K and retracing and then going to backtracking to K and then going to D. So anything which is part of separate trees, branches, cannot be part of the same graph. But D and, so for example, A and H can be, because A, H, J, A is part of the same branch. But A and E cannot be.
Yeah, it is also a correct way to get this.
Sir, one more thing, that if G and D there is an, then I will go in G, D, D to K and K to F. Then
okay,
also the main tree is getting
I'm
disturbed.
removing this. No, okay.
If there is H from G to D, G to
so
D,
which edge you want to add?
GD, DG.
GD. Okay. This one, okay?
Yeah, in that case, that tree will be GD. From D, I will get to go to K, K2
हाँ तो ध्यान में हो जाएगा.
Yeah, in that way it can be different, but if we are following the one implementation on the graph, so in that way if we are traversing K
No,
first.
if I am traversing D, then tree is
Okay.
getting changed. No?
No, but this tree is given. So we are given the tree,
क्या
DFS.
मेरे को?
So we have to work as per what is given.
Yeah, it's a given tree.
Yeah,
Yeah.
it is given that. So we will just consider this tree for to checking now. So if we are just so this is the output actually. Okay, we are getting this output. So if we are adding any another edge, so we get the same tree, or cannot get the same tree. So this is the question actually.
Yeah, we'll get the same tree, right? Understood.
We can get the same tree.
Yeah.
Okay. So when we are adding FD, in that way you cannot get the same tree. Okay, so because of that, this cannot be an edge of the final. AI, if we are adding AI, so you can see that AI, where is this AI? Okay, so when we are traversing this part, so GI, if we are adding this AI, so okay, this is the same way. So I, when we are traversing I to H, and then C, then we are reversing back, then J, then E, then A. Okay, so this is edge is not affecting the output tree, because we cannot we have already traversed I, so we cannot move to the I here. So this edge will not affect, it will remove, because it is creating a cycle. Okay, and when we are reversing back, then we are getting, for example, we are getting at this edge I to A. So we will not consider this, because it is creating a cycle, because this part is already traversed from the other side. So in that way, this will not affect the output tree. So it can be also be a part of the input CB. If we are adding CB, so in this way, so the output will be affected. In that way, you will get the like this is GK. So this G, K, F, D, and now I, and then B. So not B. So okay, when you are traversing this H side, okay, and then when you are traversing C, then you can traverse C to B directly here. So this B should become here if this edge is connected. Okay, so this B should become below C. Then you can move to the other part, J, and then E, and then A, in that way. So you can see that if we are connecting the CBS, so our output
So actually, Vasu had given a very clear, intuitive explanation, because a natural extension has to, if there are two different branches, then it cannot be the part of the same, they cannot be an edge, because it will become a natural extension of that particular branch.
Yes.
Right.
Yeah, that is also correct. Okay, now it is clear. So move to the next.
Sir, how should we approach this problem if it was a BFS?
BFS, yeah, the next one is the same. Yeah. Suppose we obtain the following BEFS tree rooted at node G. So the graph is same, but here now, this time we are performing a BFS. Do you know that in BFS algorithm, we always traverse the adjacent node first and then move to the next level.
So last question was with the DFS.
Yes, that was based on the DFS. Now this one is BFS.
One doubt: DFS is not always unique, right? We can have multiple DFS tree, right?
Yes.
But yeah, in our IIT
if any implementation is not given, then you can return the multiple DFS order.
Okay. Because according to our code, we choose a minimum. So it is always unique, right? Our IIT code.
Yes, that one. If we are following that code, we will get the minimum value in
But in
adjacent.
general, it is not unique, right?
Yeah, if we general consider the concept only, though we can traverse any adjacent.
Any, okay.
Yeah, so in that way, that is also correct.
So it depends on our code, right? If we go for a minimum selection, then it is unique.
Yeah, if code is not given, you can just follow the concept. In that way, you can traverse any adjacent.
Yeah.
Yeah, but eventually the tree will look the same, right? Because K can come on the right side and I can come on the left side, but the tree will look the same.
For any graph.
If there is a loop, then it depends on the priority what you take prior vertices. If you change the vertex, then it will go to the different tree.
So tree can be different, I think.
Yeah.
Okay, just try it. How you can think about this.
Yeah, you're correct. Only if there is a cycle, it will be different. Otherwise, it won't be. Sir, DG cannot be. What is the next option, sir? I'll see here. Sorry.
FD, AI, CB, EH.
EH. Yeah. So DG and EH cannot be.
DG and EH.
EH.
That is E. What about C option?
Even AI cannot.
And even EH also.
EH cannot be. Yeah. AI, EH.
So ACE. Okay, just check the response. So ACE, AECE, ACE, AC, AC, AC. So most of the answer are AC now. ACDE. AC. Okay, can anyone explain how you are solving this?
So may I?
Yes, sure.
Yeah. I have considered I have picked each and everything. So D and G I have picked it. So I made it like G and D should be D and G should be at next level. If G is at first level, D should be at second level. So it is not here. So I picked A is one option, and I picked the F and D. F and D should be in the same position or at the immediate next position. So it is sharing same positions. So this can be edge in the original graph, and I picked A and I. So I is at the level 2 and A is at the level 5. So this could not be edge present in there. And if we consider C and B, C is at the level 3 and B is at level 3 and C is at level 4. So this can be an edge. Likewise, I have solved it.
Okay, fine. Any other approach?
Sorry, what is the answer for CB?
My answer is A, C, and D.
A, C, and D. E, yeah, E is correct. Yeah, A, C, and E is correct answer. Okay, any other approach? By any other one? Anyone want to explain that?
See, I have a shortcut for this, but I
okay.
So
Labels are same, then we
is
can have edges.
Yeah, so anything which is like in the same tree, if there are one skip level, they cannot be together. Because if they are together, then they would have been at the same level.
Yeah.
So A and H cannot be an edge, for example.
A and H
cannot
be. Yeah, okay, yeah, fine.
Excuse me, sir.
Yes.
So here can we say that the cross edges are possible, but back edges are not possible?
So this is not a directed graph.
Yeah, but still, sir, there are Like back edges, I mean from C to I or from H to I, something like that.
No, for example, if we are connecting C to B,
Yeah.
so what type of this edge?
So I think it's in the different branches. So it is a kind of cross edge, I would say.
So here this is not actually a directed graph. So cross edge, back edge, I think that we consider for the directed graph.
Here, example of D, we can explain like C and B can be connected because by connecting that, our level of C will not change.
Level of C
will not change. Like here from H is connecting to C, and H and B are on the same level. So if B is connected to C, so if I explore with B to C, then it will be on the same level.
Okay.
Will it change? What will happen if we connect K to C, like cross connect?
K to C. Okay. So it
No,
is possible or not?
I didn't understand the CB one. C, if C was connected to B,
It's possible. Like
it can be connected actually.
yeah.
It can be. Level will not change on the tree, right?
But sir, B is one level up than C, I think.
So
Yeah, that is the trick. Yeah.
level difference must be at least like it should be like at most one. It should be at most one.
Yes, correct one. Okay, so for example, if we calculate the distance from the root node, okay, so or in the starting node. Okay, so for example, if we calculate the distance from the root node where from we are starting, so if you see that what is the distance for this two node K and L, this is a, if we are considering the number of edge, okay, in the distance, so the distance for this level is 1, and the next level is 2, and next level is 3, and next level is 4. So any edge cannot be part of the original graph if the difference of the distance is more than the absolute value of the difference is more than 1. So for example, if we are connecting this AB, okay, so what is the distance for B is 2, and what is the distance of A is 4. So if we calculate the absolute difference, we are getting 2. So this is not possible. If we are getting less than 2, so that is the possible. Okay, so you can use this trick for that.
Less than, if you're getting less than 2, then it's possible.
Yes.
Basically, more than 1, it's not possible.
Yeah, more than 1
More
is
than
not
1
possible.
is not possible. So
Absolute
DG,
value, absolute difference value. Okay.
DG is also not possible.
So D and G.
Yeah.
This is also not possible. Here, this is the 0, and this is 2. So 0
Right.
minus 2 is, this is also not possible.
So the final answer will be 4 of these edges are not possible. DG, AI, CB, and
No.
EH.
First one is DG.
Yeah.
Yeah, so A is correct answer. This is not possible, but B is possible. AFD.
B is possible, yeah, but C is not possible.
C is not possible. D is
not.
D is possible because you see that this is the level 2 and this is level 3. So 3 minus 2, you are getting 1.
Okay.
Okay, so this is possible. And EH, so EH, the difference is 2, more than 1. Okay, so you can use this trick for. Okay, so this is the one. Okay, just tell me the answer. I think you can quickly give the answer for that.
To find adjacent vertices.
Yeah, find adjacent vertices of any node. Which of the following is representing the complexity to find adjacent vertices in adjacency matrix and adjacency list. Yeah, adjacent vertices of any node you can consider here.
Of any node, one node.
Yeah, one node. I think this word is missing in the statement. Adjacent vertices of any node.
Matrix it's ON for sure, but for adjacency list.
I think you have already used these neighbors algorithms in any algorithms of Big Four.
List will be O1.
O1. Yeah. So generally we implement the list using a dictionary, and matrix we generally create by the adjacent nested list or NumPy array.
No, but to identify all vertices, I have to still go through the values of the in the dictionary, right? So let's say I have vertex 1 I want to understand. Whatever are the values, whatever that list is, it could be a smaller list, but I have to still go through the overall thing, right? I have to go through that to see what are the vertices.
So I think that value can so adjacent node, you can find the all list in the constant time, complete list.
So this is basically you are finding is search. We put search, searching for a particular index, right?
Yes, index. So what are the adjacent? So in
so that'll be O1 only for list, for
Yeah,
adjacency
O1.
list, right?
But big O and for matrix, because we have to traverse all
Yes.
the columns.
All the columns, right?
And we have to check which contains the value 1. Okay, so in that way, so maybe if, for example, if we have 10 vertices in the graph, but 2 are connected, still we have to traverse all 10 in adjacency matrix. Okay,
how
but
is it list? How is it a constant time, sir, in the list?
Constantly list, you can directly just check the index, which node you are finding the adjacent. You can directly traverse. You can find directly by the key in the dictionary, and you can just return that these are the.
Oh, that
adjacent.
way. Okay. Sorry. Yeah. Correct.
Okay.
Basically, the keys are only to be found in
Yes.
in the list, right?
So option A is most of the answer. Okay. Now this is the next one. Okay, think about that, how you can perform this operation. Previous answer is option A. Someone is asking, I think. Yeah, option A is the correct answer. And 1.
Sir, previous options one, sir. Previous slide.
Okay, 1 second. Yeah, previous is A option is correct. Okay, we can find out the all adjacent in big O and time in the adjacency matrix, but in adjacency list we can directly get this in constant time.
Yeah.
Okay. So this is the next one. Okay, so I've received 20 response. Okay, C is the most one, and D is also is 6. Okay, so C is the most one. Okay, so can anyone explain what approach you are using for option C?
For each vertex, there are n vertices. For
Hmm.
each one of them, you have to add the adjacency list, like how many counts are there, right? Amortized, it will be n plus m.
N plus M. Okay. So here, okay, 1 second. Yeah. So here one adjacent. What happening? Yeah. So here one adjacency list is given, and we want to compute for each vertex. We want to compute the set of incoming edges. Okay. So in our adjacency list, we generally contain what are the adjacent of each node. But for incoming edges, we have to traverse all the value of dictionary. So in that way, so in n steps. So for example, if we have a vertices n vertices, so we can create another dictionary for each vertices, and then we can traverse all the edge in our adjacency list. Okay, so we can simply traverse all the edge in our dictionary, which is given in the adjacency list, and we can check that what are the so we can check the value part only. Okay, so that is representing a number of edges. So which value is correspond to which key, that means the edge is coming from the key side. Okay, so that information we can store in our dictionary. So n time is required for generating another dictionary for n vertices, and m time is required for the visiting all the edge in adjacency list. So in that way we can perform this in big O n plus m time. Is it clear?
Sir, could you explain again?
Okay. So for example, if we have a one adjacency list in that way, okay. So for example, we have an adjacency list, and one like it is given that so 1 2 3, okay, in that way. So 1 2 3 4. So 2 3 and 4 and 0 3 and so not 3 4. Okay, so 1. So like that, we have one adjacency list. So it is representing that what are the adjacent node of each node. So the adjacent of 0 is 1 2 3. So that means the edge is going from 0 to 1, 0 to 2, 0 to 3. Okay, so this is outgoing edge, but we want to calculate the incoming edge for each node. So we can create another dictionary for that. So for example, another dictionary A1. So we are creating, and then we can create a key value combination 0 1 2 3 4. Initially all are empty. Okay, so it will take n because number of vertices are n, so it will take the n time, but after that we will traverse all the list. Okay, we will just traverse all the value from this side. So this is representing a number of edge. Okay, so this all value, if we count the all value, okay, so 1 2 3 4 5 6 7 8 9. So this 9 is representing a total number of edge in graph. So we need to traverse all the key value combination, and in the value combination we can just represent it. So for example, if we are traversing the first key value combination, okay, so in that way we can say that so incoming edge, so for this one, there is one edge is coming from 0 side, so we can contain this value here. Okay, so 0 to 1. So this is the first. Okay, now we will check the second is 2. So that means one edge is coming from 0 to 2. So we will store this value here. So 0 to 2 in that way. Okay, so another is coming 0 to 3. So we will store this 0 to 3. So that means we have to require to traverse all the value in adjacency list. Okay, so it will take m time. Okay, so the number of edges m in our question. So in one traversal of number of m times, so we can store this information in our output dictionary. So what are the incoming edges for each node? So n time is required for creating this one, and m time is required to traverse all the values from adjacency list. Total time is n plus m, big O n plus m. Okay. Is it clear?
Yeah, it's okay.
Yeah. Okay, so correct answer is C for this. Yeah, this one. 20. So for this question, so I think someone is asked in the previous. So if any code is not given, okay, so you can consider any adjacent first.
Okay, yeah.
Okay,
I asked, yeah.
This one. So DFS we are performing from node A here, and which of the following is our possible outputs? So this is MSQ. So I don't know what type of options are you are getting for this. Okay, so this is the text box. So if we are performing DFS here, so you can select any adjacent. Okay, if you are getting more than one adjacent, you can select any. So that's are possible according to the concept. If code is not given, you can pick them. Okay, I've received 20 response. I'm checking the answer. ACD, ACCD, ACD, 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 ACD. Okay, so most of them are ACD, ABCD, ACD, ACD, ACD. Okay. Okay, so how we can check that? If we are starting from A, okay, we are performing. Sorry. Not here. Yeah. If we are starting from A, then we are performing DFS algorithm. So we can pick any of them. So we will just check by the option. So A, B, E. Okay, so A we can pick, B, and then E. Okay, so E is also connecting the adjacent of B. E, then G. Okay, so G is also connecting by E, and then H is connecting in that way, and F. Okay, so we can traverse. Okay, so this is correct. Now second is A, B. So A, B, and BF. Okay, so we can move to BF. Okay, correct. Then FE. FE is not possible. Okay, so there is no S connected by F to E. So because other are connected by F, so we can traverse H and G. Okay, without traversing this H and G, we cannot traverse E directly. So this is not correct. ABF is corrected according to the depth. So then E, no, H. Yeah. H is correct. Then G, then E. Yeah, this is correct. And AFG, yeah, G is correct in that way. And then H, okay. And B is okay. And then E, yeah. So we can traverse according to the depth wise. So option A, C, D is the correct, but we cannot perform the B. So B is not the correct way using the DFS. Okay, now next one is BFS. The same question using the BFS. So in BFS algorithm, we can traverse adjacent node first, then we can move to the next level. Okay, just check this concept. It is following in the option or not. So here you can also select any adjacent first if code is not given.
Excuse me, sir.
Hmm?
Sir, is this the only session?
Yeah, this is the only revision session for PDS.
Okay, sir. So more questions you will be discussing here?
Yeah, sure, I'll discuss.
Okay, sir.
Guess we are not sleeping today. More questions will take maybe about 1 hour.
So if you have already solved mock questions, so no need to check again. If you have any doubt, you can ask.
Sir, is it if you have the solution somewhere, you can just share it, na, sir?
No, I don't have solution.
Okay.
So
but most of the questions are discussed in discussion forum.
Yes. Yeah, I pasted in the discourse in someone post reply. You can ask on the discourse, so we are replying on that. So many questions are already discussed, so you can read that post. So learning from the solution is, I think, it is not a good way.
So in this course, I found only question number 10 and 13.
No. Another question is also available. 7 and 8 is also available. Okay. Yeah, we will discuss. If you have any doubt in any particular question, so we will discuss.
Okay, sir.
Okay, so for this question, I have received. So this is the same one as the previous one. So AB, CD, AB. This time, okay, the different solution I'm getting. AB, ACD. AB. Okay, so AB is the most one. Okay. So for this graph, where is the graph? Not this one. This one. So here we are performing BFS algorithm. So if we are checking the option A, B, E, F. Okay, so A, if we are starting from A, so what are the adjacent of A is E, B, F. Okay, so these all three are adjacent of A. So we have to traverse all three first. But we can traverse in any order because any code is not given. So concept wise, we can traverse any one. Okay, so A, B, E, F. So in this option, B, E, F is traversed after A. So that is correct. Then H and G. Okay, so H is connected by F and then G. So the first option is possible. And second option A, B, F, E. Okay, so B, F, E. So that means we are traversing A, then B, F, E. After that, we are traversing H, G. So this is also possible. And A, B, F. So A, B, F. Okay, now H. So without leaving this E, we cannot traverse any other node because okay. So this is a adjacent of A. So we have to finish all adjacent first. So here we are traversing BF and then we are leaving E. Okay, we are traversing H. So it is not possible in the BF according to the BFS concept. So this is the wrong one. AFG. So A, F, and then G. So here we are not traversing the adjacent B and A. So this is also not correct according to the BFS concept. So this only A and B is the correct answer for this. Yeah, next one is this. Okay, so this question is a little bit time consuming. You can not return the answer quickly for that. So, but can anyone explain how you can solve this? What approach you can use for that?
To use a topological sort, I think, because it's got constraints.
Yeah, so here some dependencies given.
Dependencies, yeah.
So the approach to solve this question is just create a DAG first based on this dependency. And then after that, you can perform the topological sort. Not topological sort actually. Here we are just giving that we can remove so here there are enough electrician to rewire as many room as can be rewired in parallel. Okay, that means if so in the terms of DAG, if more than one nodes are available within degree 0, so you can remove all the nodes at the one time according to this question.
This will require longest path because we have to do in minimum number.
Longest path? No, not longest path.
Then why is it asking
here,
minimum number?
Yeah, minimum number. Actually, here this condition is given. There are enough electrician to rewire as many rooms as can be rewired in parallel. That means,
parallel. Okay.
Yeah, so we can remove all the nodes which have integrity 0 in the one unit time. In the question concept, we can remove all in the one day. We can complete in one day because we have enough electricity.
Right.
So what is the answer to this question?
Okay, so only 4 responses.
4. Is it 4, sir?
No.
So here we can only start from 10 or 11, right?
First we have to create a DAG for this. So I have also not a direct answer for that. Okay, so this dependency is given. After that, we can create a DAG. So just created nodes. So total 11 are there. Okay, so we can start from any. One must be rewired before.
So let's start from 10 or 11.
We can start from anywhere and then we will link. Okay. So we are starting from here. Okay, so one must be rewired before room 3. So that means like this 3 and 4. Okay, so this is created by 1. 2 must be rewired before room 6. So we are just connecting this 2 by 6. 3 must be rewired by before 5. So 3. Yeah. So this one is already there. So before 5. Okay. 5 must be divided before room 8 and 9. So 8 and 9 is not there. So 8 and 9. And 6 must be divided before room 7. So 6 is okay. So this is like 7. 7 must be divided before room 5. 5 is there. So we can connect in that way. Okay. 8 must be divided before room 10. And 9 must be divided before room 11. Okay, so now this is a DAG we are getting from this dependency. Now you can see that what are the nodes which have in degree 0?
1 and 2.
2.
1 and 2.
1 and 2. Okay, so we can complete these two in one day. Okay, so we can perform in one day, and so that means we can remove both in the one time. After removing this, what we are getting? So we are getting this. So I'm removing this now, this edge and this edge. Okay, so yeah. So how many number of nodes are available within degree 0 now?
3, 4, 6.
3, 4, and 6. So we can remove in one day. Okay, when we are selecting this, so we just remove this both edges. Okay, then now 5 and 7 we can perform.
7 only.
No, not
Only
we
7.
cannot perform. Yeah, only 7 we can perform. Yeah, so this is 1. Okay, when we are selecting this, we are removing this edge. Now we can remove only 5. Okay, so this is one more, and when we are selecting this, so that means this we are getting. Now we can remove in one day, and when we are removing this, now we are getting this one. Okay, so 1. So 1, 2, 3, 4, 5, 6 stages required to complete this. Okay, so this type of question, just create a DAG diagram first and then just perform this topological sorting concept according to the condition which is given in the problem. Okay, next one is this. Yeah, this is based on some graph property.
Now the previous one, will it not be the longest path again?
If you longest.
If you work on the longest path, that will be 6 again. 2, 6, 7, 5, 8, 10. That is the longest path.
2, 6,
7, 5, 8, 10. So that is 6. 1, 2, no.
But here we are asking the number of days are required to complete. So some conditions are different. So maybe longest path.
Longest path will give no number of days, ne? Because
yes, I think it will give the correct answer also.
Then it is 5. Then from where is this? 6?
No. So you are starting from 2 now.
2 if you are starting 2, 6, 7, 5, 8, 10. So that is one longest path. Okay, all longest paths are
6.
5.
If you are starting from 2 to 10, it will be 6.
No,
2, 6, 7,
5.
then 5, then 8, and then 10. It will be 6.
That is 3 plus 2, 5 only.
No, 6 only.
6 only. 6 vertices you have
2, 6, 7,
Oh, sorry.
5, 8,
It is 6. Sorry, I was counting the edges. That is right. Edges 5. Okay, 6 vertices.
Nodes are 6. Yeah, you can use the longest path approach also.
Yeah, longest path is the right answer for that.
Mm-hmm.
Okay, I was counting the edges. Sorry.
Otherwise, quickly you can use this approach.
Yeah, that's so obvious. No, this is normally this approach is being taken for the task management, that the serial task and parallel task.
Correct. Yes, correct. Okay, so this is the next one, 23. So based on some property of the undirected graph, and you can simply observe these things. So 12 I have received the answer for that. Okay, 19 I've received. So option A, C, E, B, B, A, O, B, C, A, B, C, A, C, A, C, E, A, B, C. So yeah, for this I'm not getting the correct answer. Okay, so for first option, so just because we have undirected connected graph. Okay, so in the undirected connected graph, every edge contribute 2 degree. Okay, so every edge connected between two vertices. Okay, and it contribute 2 degree in the overall all degree because it is connecting by two vertices. So that means if you have any number of edge, so for example, if you have 5 number of edge, so definitely it will contribute 5 into 2, 10 degree in the overall graph. So that means in that way you can select the option. So the sum of the degree of all vertices is always even. So this is the correct one answer. Okay. And second option, the number of vertices with odd degree is always even. So for example, if you are taking this odd, okay, so odd degree means, so for example, if we have a degree 3 for any vertices, okay, and you are just considering this 3 for the odd times, so you will get the odd total degree odd. So that is not possible in the sum of all degree. You are getting the even numbers degree for for the complete graph. Okay, so in that way, so number of vertices with odd degree is always be even. This is also a correct. Otherwise, you can get a odd number of degrees for overall graph. So this is also true. In a complete graph.
So can you explain this again?
So for example,
in a graph, in some graphs, some examples.
Okay. So if we are considering this graph, A, you can create any graph. Okay, so you will never found that the number of nodes which have odd degree is odd. Okay, so for example, if you are saying that the number of nodes or degree is 3, so if you will add all the in degree or all the odd degree. Okay, so for example, someone contain 3, then someone contain 5, and then one contain is 7. Okay, so our you are saying that the number of nodes which have odd degree are odd. So in that way, if you are summing this 3 plus 5 plus 7, what value you are getting? 15. This is an odd value. It is not possible in the graph because remaining, for example, for remaining edge, so that contains the even degree. So that means the sum of all degree will remain the even. Okay, so if you are contribute that 3 nodes have the odd degree and 5 node have the even degree. Okay, even degree. So that means if 5 multiply even degree, you will get the even value. Okay, so here you will get the odd value. So even plus this 15, you will get total odd value. This is not possible because in the first statement it is the true. The sum of the degree of all vertices is always even. So you cannot find this odd value for. if you are selecting this condition. So this is also true. The number of nodes which have odd degree will always be even. Then you can get the sum of all odd value will be even. Otherwise, you cannot get.
So, but undirected graph, how can a node have odd degree?
Yeah, that is possible. So, for example, like this is E. Now this node contains odd degree. Okay, so if you see this in this graph, so this contains 1 degree, this 2, this 3, and this 1, this 1. Now you can see that number of odd nodes are, how many numbers of nodes which have odd degree? 4.
So
And
is
one
the
is
same
even.
edge not representing the in and out both the degrees?
No. In the undirected graph, we just consider the degree, not in or out. Here is there is no meaning for in or out.
Okay.
Okay. In the directed graph, we just consider this term in degree and out degree. But in undirected graph, we just use the degree, which are incident on nodes. Okay, how many number of edges are incident on that node? That is called the degree of for that node. Okay, so in that way you can see that so this number of nodes which have odd degree will always be even. Then you will get the sum value will be even. Okay, so the first statement is correct, and based on the first statement, second statement will always be correct. Otherwise, if you will not consider the second statement as a correct, then you will get the first statement will also be incorrect. So that is not possible for undirected graph. Okay, so first option is correct and second option is also correct. In the third option, in a complete graph, the degree of all vertices are equal. So that is true, because when you are creating a complete graph, that means every edge is connected by remaining edge. A, B, C, D. Okay, so if complete graph means every vertices are connected with remaining vertices in that way. So this is a complete graph. So here you can see that the 3, 3, 3, and 3 all will always remain the same number of degree. Okay, so in any node, if we are connecting in that way, so this is also a same degree. So option C is also correct. So option D is the reverse of option B. The sum of the degree of all vertices is always. So this is a reverse of option A. This is not possible because every edge is contributing a 2 degree in the graph. So it is not possible. So the number of vertices with an even degree is always even. So this is not a true. Even degree is always even. This is not true because we can just take a counter example for this. So in the first example, you can see so it contains even degree, but the number of nodes is only 1. Value is 1. Okay, so even number of nodes which have degree even degree. So this is not a, or it can be odd, it can be even. So the option E is also not correct. So only option A, B, C is true. Your next one is this. So this is based on the DFS tree. DFS, we have already seen that. Okay, so multiple combination of answer for this. Okay, after seeing the display, you're changing the answer. Okay, so now we have received the 10, option B by the 10. So can anyone explain? Yeah, can anyone explain this?
No, the option B only need an explanation, no? Right? Because the question itself is saying very clearly the V be the next visited vertex.
Yes.
So you has to come first. So you has to come from you coming first means V is the descendant.
But UV need not be an edge, right?
It has to be. No, next visited means it has to be.
It need not be, because once it is a leaf, you are going back to the parent.
Not only that, it says must be an edge. It need not be an edge. That should not. That's wrong. Right?
The next visited, if you see, okay. This was discussed yesterday, right?
So let U be a vertex in G, and let V be the next visited vertex after visiting U in the traversal. Okay, so it is talking. We are talking about the traversal here. So which one is the always true? So UV must be an edge. So this first statement is always be true. Just check the first statement. We are not moving to the second statement. Here this is given UV must be an edge in G.
Okay. That then the right answer is D.
Sir, if UV is not an edge, then in DFS it cannot traverse. No?
Yeah, it can
No,
traverse.
so,
it can go back
It
and
can go to the other branch, right?
So
After
isn't C always true?
C.
Yeah.
Yeah, C is the correct answer for this.
If UV is not
If UV is not an edge in G, then U is a leaf in T.
Yeah. That is right. This yesterday we were debating. I'm actually in half sleep mode now. That is why.
Okay, no problem.
Yesterday I only pointed out that it is C. C is correct answer.
What is meant by leaf? Can you please explain?
So leaf is the last node. Last traversal node. Okay, so after that there is no node available for traverse further. Okay, so that term is used for leaf. So basically it is based on the simple normal tree. What is the leaf? So you cannot traverse after that. This is the last point. Okay, so I think it is clear for everyone. So for example, if we have a tree A, B, C, like that will be. So yes. So for example, this is a graph. Okay, I'm traversing this one from A. Okay. So the first condition in option is given. So in the original graph, so we are traversing. The statement it is given. So for example, if we are traversing D, and after D we are traversing E. Okay. So after T we will traverse E. So when you are traversing, then in that way, B, then C, then D, then you will traverse E. So we are traversing E just after D. So for this situation, you can just find the answer. So in the first statement, UV must be an edge in G. So this statement is not true for this example. Okay. So original graph, so there is no need to link by this D and E. Must be an edge. So same things for the B option is also incorrect because UV must be an edge in G. This is not always true. And in the D option, if UV is not an edge in G, then U and V must have the same parent. So this condition is looking correct for this situation, C and D. Okay, so we are traversing B to C, and then we will traverse D. So D after C. So in that case, the parent is same, but that is also not always true. So in that case, for example, D and D, so the parent is not same. So option D is also not always true, but you can find out that if UV is not an edge in G, then U is a leaf in T. So that is always be true, because you can see that if we are traversing C and D after just C, so you can find out if C and D is not an edge, then you will. So that means we are completing one depth completely, and then we are moving back, and then we are traversing the next depth, next part. So in that case, so we are reversing back from this side. So this is a last node, then we are traversing, and then we are moving to the another branch. So in that case, this will always be a leaf node. So if C and D is not the edge in the graph, so this is the possibility for when we are traversing D just after C. So you can see this in that way. So here D is also a leaf node. There's no another node are available. So option C is the correct one. Yeah, last one. This is the last one. So I think you can remember this in the pre-post numbering. So where some cross edge and back edge and forward edge is discussed. So this question is based on that.
You're not getting the answer box.
Oh, for this one? Oh, okay. Yeah, this not set. You can just paste the answer in chat box for this. B, okay, so this is the latest one, okay. B, okay. B. Yeah, okay, fine. So B is the correct answer for that, because we know that, so if you remember this, yeah, this is the forward edge, back edge, and cross edge condition is given. If we are calculating the pre and post number for any graph, okay, so we can directly find out that which one is the back edge, which one is the forward edge, and which one is the cross edge. And back edge is always create a cycle in the DFS tree. So we can just check this condition. If interval pre of V and post of V contains the range pre of U and post of U. So if the pre of V and post of V, so this range contain the value pre of U and post of U. That means this is a back edge, and back edge is created a cycle. If you see the diagram, okay, so if you see the diagram, this red edge representing a back edge, so it is created a cycle. So you can remember this condition for that. Okay, so in the question, it is this condition is given. So if UV is an edge of a graph such that pre V and post V contains the pre-U and post V, then the graph is necessarily a cycle. So that means graph contains a back edge and back edge representing a cycle. So this condition is true. B option is true for that. Okay, so now the all question have discussed, which I have. Now we can discuss the another question. If you have any doubt, we can discuss.
So can you explain the question, the stable one in the sorting that you explained?
Which table?
Stable, that question which contained the
question.
stable.
So is there any query in this question? 25? Or can we move to the back? Okay. So stable, this one is the initial question actually.
Yes.
Selection sort. On this one. Oh, where is this? Yeah, this one?
Yes.
Yeah. So selection sort is not a stable algorithm. So first thing you should remember these some basic properties. So I have mentioned this one. Yeah, here. So these are some basic parameters are given and value are given for sorting algorithms. So just you can remember for the quick answer. Okay, so selection sort is not stable. So what is the meaning of stable? Stable, so definition is also given. Okay, if we are taking any input which contains this more than one element which has the same value. Okay, and our sorting algorithm is generating a sorted output. So in the sorted output, if the order of similar element is remain the same in all so always remain the same for every input, so that algorithm is called the stable algorithm. Okay, this is clear. So for example, you can see the first list, A option. So here you can see that there are two elements which contains the value 4. Okay, so this is the input. This is the input for selection sort. So it is always possible our selection sort will remain the so this order should not be changed. Should not be changed. The first 4. Okay, so I am explaining with the on the here now. So for example, if we have a list, so I'm just explaining with the small examples. Okay, so 3, 3, 2. This is one input. Here you can see that there are 2, 3 are available. Okay, so just I mentioned that this is a first one and this is a second one, B. If we are giving this input into any sorting algorithms, and our sorting algorithm will always return the sorted outputs, that means our output will be this like this 2, 3 and 3. Okay, so in our sorted output we should get this A first and this B second. So this order should not be changed. So this order should not be changed like this 2, 3 and this become B and this A. Okay.
Okay.
If we are getting this type of output, that means our algorithm is not returning a stable output.
Okay.
So order of similar elements should not be changed. If our algorithm is following this rule, so that is a stable algorithm, otherwise not. So for example, if we are giving this input to our sorted but to the selection sort. Okay, so how our selection sort will work for that? So selection sort will select the minimum element. Okay, so in selection sort we just consider that this is a minimum element, starting element. Okay, after that we start the comparison. We just find out that what is the smallest element in the list. So we start from the first element, then compare that is there any element available which is lesser than this. Okay, and then we will update our smallest element. So we will start from this 3 and then we will check the next element. So 3 is not less than 3. Okay, so we will just consider this is a smallest element. Then we will move to the next element. So now we will check this 2 is lesser than 3. Yes. So we will
Yes.
just shift this as equal to this one. Now we have completed the list. Now finally we get this. This is a smallest element in our list. After that, we will just swap that this element by a first element. So when we will swap this one, so our 2 will come here and 3 and 3. Now this 3 is a B and this 3 is a A.
A.
Okay, because we are
Not
swapping
stable.
this one and this is coming at this position in that way.
Yes.
And after that, so after this first iteration, we are at this stage. So we are getting that this is a smallest element, and we are comparing the next element. Our next element is smaller than this one. No, so we will not perform any swapping operation. Now we will so same in the next element. So this is the last element, so we will not perform anything. So after the completion of the selection sort, we will get this output 2 3, and this 3 will be B and this 3 will be A. Okay, that means our order of similar element has been changed.
It is not stable.
It is not stable. So these things we are checking in our for this question. So here you can see the four element is repeated in the each option. So 4 4 4 4 4 4. So just apply this concept in each option and check that for which option our selection sort is returning a stable output or not. Okay, so this is not always true. Okay, our selection, so this is not always true. Our selection sort will always remain the unstable output. It may be written stable, it may be not written stable. For any input, if it is written not a stable output, we can see that this is not a stable algorithm.
Excuse me, sir.
Okay. So
Yes.
yes.
So, sir, can we say that you are generalizing a sort, like so insertion sort is stable or not?
Yeah,
Or
insertion
selection?
sort is stable. So these are
We
some
can say that.
property. Yeah. So insertion sort is always return the stable output. Yes, someone is asking in between. Yes.
Yes, sir. Sir, please explain question number 10 from quiz mock.
Mock quiz. Okay. Okay. So is this clear?
Yes, sir.
Yes, sir.
Okay. So mock question. Okay. Question number 10. Yes, someone is talking. No, your audio is very low. I'm not. You are not audible to.
What is the sixth question answer, sir?
Sixth question answer for this one.
Yes, sir.
Okay, so sixth question answer is so this okay 2 to the power n is the complexity.
Okay, sir.
Okay, and the recurrence relation will be Tn equal to 2 and T n by n minus 1 plus 1.
Okay. Order of n, sir?
Now complexity is 2 to the power n.
2 to the power of n.
Yeah, recurrence relation will be like this: Tn equal to 2T n minus 1 plus 1, and complexity will be we go 2 to the power n.
Okay, sir. Thank you.
Okay, so this is the answer for yeah, mock person we are talking about. So okay, mock unit and question number 10.
Question 10. Yeah.
4 5 9. Okay, this one. Okay, so here some steps are given, so we have to follow each steps one by one. Okay, just wait. Okay, so what we are doing, so any other things remaining the question? Yeah, so this part is also. To consider a list of n integer with many duplicates. Okay, so list have many duplicates such that the number of distinct integer is in L. In L is log n. Okay, so distinct integer is log n. So just pointing this distinct integer we have log n, and total elements are n. Okay. We use the below algorithm to sort this list. What will be the worst case asymptotic complexity of this algorithm? Okay. So now first step is iterate over all elements of L and create an array A1 of all distinct element in L. So we are just iterating the list completely. Okay. So what will be the complexity for this part according to you?
So big O of n.
Big O of n, because the size of L is n.
Yeah.
Okay, we are iterating completely this list, so definitely the complexity will be big O of n for this. Now this is the first one, and we are creating a list. We are creating an array of distinct elements. Okay, that means it contains a log n elements. A contains a log n elements. Correct?
Okay, sir. So instead of n, we have to write log n.
The size of A is log n.
Yeah.
Okay. Now we are performing sort the array A1 created in step 1. Yeah, we are performing sorting for A1. And hint is given, if the size of A1 is S, then the step takes S log S. So for example, we are performing a sorting algorithm. It takes S log S time if input is S. So here input is log n. So what will be the time?
So it will be log n of log.
Log n and
log n. Log of log n. Yeah.
Okay, in that way.
Mm.
So this is the complexity for second part. Step. Create another array A2 containing all 0 equal in the size to A1. Okay, so we are creating a A2. This one is a A2, and the size of A2 is also a log n. Correct?
Yes.
So that contains all 0 equal in size of A1. Now we are just traversing the list L. Okay, so for each element in element E in L, using binary search, find position. Okay, so we are applying the binary search on A1. Okay, but we are traversing this list L that contains a n element, and we are performing a binary search on A1. So that contains a log n element. Correct? So binary search, if you are performing binary search on log n element, what will be the complexity?
It will be generally it will be n log n, so it will be log n and log of log n.
Binary search, it will be
log n.
Log n. Log n.
So log n we are generally take, but here the size is log n, so this will be log n.
Oh, so instead of n we have to place log n.
Okay, so this complexity is for only this part. Okay, but we are performing this operation for every value of L. So what is the input? What is the size of n? So we can just multiply this n in this part.
Then it will be n log n.
Yes. So okay. Also that we are performing another operation. Increment the value of position P in A2. So we are just incrementing the value of that means we are just counting the frequency of each element. So this is we are performing. Okay. So this is a simple operation. This is taking this time. So we can decide the final complexity for this part. So this will be a n into log n. Correct?
Yes.
Okay. Now next one is initializing a new list ls. So this is a constant operation. Now created a sorted list using A1 and A2 for each index I of array A1. Append. Okay, so here we are traversing a A1 list. Okay, so that contains a log n element, and we are just we are creating a new list. Yeah, so appending A2 I times. So that means we are simply appending. We are using a appending operation. So overall, it will take total number of elements are n. and we are performing this. Yeah. So this create a sorted list using A1 and A2 for each index I in array A1. We are appending it, we are creating a A2 list. So this operation will take total number of n times, because we are what we are doing. So one list we have a distinct element. So for example, like this 1, 2, 3, 4, 5, and second list contain a frequency of each element like 2, 5, 6, 3, 8 is this type. Okay. So we are just creating a final sorted list.
Yeah.
Okay.
So
So
this will be n log n, the step 6.
Not so appending A2I times value in A1I.
Append will
A1I.
be 0 O big O1. So that is not. But the line 6 should be n log n.
Creating sorted list using A1. Okay, so here this ls is created. Okay, so here we are creating this inside the ls. Okay, so we have ls is empty list. Okay, and here we are reading the element 1, and for 1 what is the frequency of this? 2. So we are simply appending 1 1. Okay, now for second value, what is the frequency of this? 5 2 is 5. So we are appending 5 times 2. 2 2 2 2 2. Okay, same way we are performing this 3 3 3 6 times. So you can see the total number of operation will be, if you count the length of this list. So this list counting is representing a n. Okay, so this is representing a, you are taking this 1 2 times, 2 5 times, 3 6 times. So if you add all these, so the total size is representing a actual input size n. So that means it is taking a number of n steps.
So total input size is n. So we have a log n distinct elements.
Yeah.
So
So but
it
we are
means it means
creating a new list. We are creating a new sorted list. So for every value of this one, we are reading a frequency and then we are appending the elements here in the output list, sorted list.
okay.
Okay.
So we are having n elements, and out of which log n are distinct, and we also
Yeah.
have duplicates.
Yeah, basic purpose is this. We have a list which contains the duplicate value, and we have to sorted this list according to this algorithm.
Okay.
Okay, so this step is taking n times, because if you consider, if you multiply the steps, so for this 1 and multiply by 2, 1 into 2 plus 2 into 5, okay, plus 3 into 6 plus 4 into 3, 4 into not 4, okay, okay, so I'm not doing in the correct way. So for each value we are performing, okay, so for this value we are performing 2 steps. Okay, we are performing 2 time append operation in this list. For second value we are performing 5 time append operation in this list. Okay, so 2 then plus 5. Then for third value we are performing 6 time append operation in this list. Okay, so next is 3 time append. Okay, next is 8 time append. So what is the total number of steps? This will be equal to n. Okay, so this step is taking n time. So 6 step is taking. So which one is the largest one? Now question is this.
Okay, so it is n log of log n.
N log n.
So sir, in binary search, we generally have the order of log n. So instead of here we have log n distinct elements. So we are putting log of log n, and we are
Yes.
multiplying it by n because we have total numbers as n.
Yeah, we are traversing this list now. So if you see the fourth steps, we are traversing each element in L. So this is contain the size n, and for each element we are searching this e element in our distinct list.
So for each element, we are performing this binary search, and this binary search takes log n steps, and so that
Binary search taking log n step, because size of this A1 is log n.
yeah, okay. So it is log n. So when we both of things got multiplied, so it becomes n log of log n.
Log n, yeah, this one.
Okay, so
So this is the largest steps. So in the when we are performing this operation sequentially, so we will select the largest value for the complexity. So this will be the answer.
Okay, so okay, thank you.
Yeah.
So remaining question I understood from the discourse forum.
If you have any specific query in any particular question, you can ask. Yeah, Oma?
15th one, can you scroll down? I'm not understanding from the discourse forum also. That's why.
Okay, so 15th one. This one?
Yeah.
So here one, okay, copying this one. Yeah, here one matrix is given. Okay, so in matrix, the entry of each row are sorted in increasing order from left to right. Okay, so and the entries in each columns are also sorted in the increasing order from top to bottom, and the first element of each row is greater than the last element of the previous row. So that means we have a list which is sorted like this. So 1, 2, 3, 4, 5, 6, 7, 8, like this.
Yeah.
10, 15, 16. In that way. Okay. Now we want to search any elements. For example, if we are searching in 11. Okay. So in that way, how we can find out the correct answer? So first thing, so we can search the first element. So for example, we can access the first element and last element in the single step of every row.
I'm not getting. Please repeat.
So for example, if we have a matrix, so this contains a 0, 1, 2, 3 index, and this also contains 0, 1, 0, 1, 2, 3. So if we have a matrix n by m size, so we have a size. Okay.
Yeah.
So we can pick the first index and last index directly according using this size.
Yeah.
Okay. So for example, first we will apply the binary search on the row.
Okay. Yeah.
Okay, row, and we will compare the elements which is coming in range or not of the first element and the last elements which is coming in between or not. So
Yeah.
for example, we will check that what is our searching element is 11. Okay. Now we will check that this 1 and
Yeah.
4.
Yeah.
So our element is greater than, lesser than, or in between.
Yeah.
If it is greater than the last element, we will move to the
Next.
okay, for binary search we will not start from the first, we will start from the middle element. Okay.
Yeah.
Okay, so for example, we are selecting middle as this row.
Yeah.
Okay, so we will just check that if our searching element is greater than the last element or not, or the smaller than the first element or not.
Yeah.
If it is smaller than the first element, then we will discard this part.
Yeah.
If it is greater than the last element, then we will discard the
this part.
part. Okay, so in that way we can apply the binary search on the row first.
Yeah.
Okay, so in for example, this is a size n and this is m.
Yeah.
So you can apply you can find out this row which you have to search in log n step.
Yeah.
According to the binary search, after getting the row, you can apply the binary search on columns. So for example, after getting this row, this is also sorted, you can apply the binary search on this part. So this is a m size, so it will take a log n step, log m step.
Okay. Okay.
Okay, so this is the one log n plus log m. This is the one possible. So this is the one correct answer, and it can also be represented
Yeah.
by
Depends on log. Yeah. M into n. Yeah.
yeah. So both are the correct.
I have one more question in the discussion forum. Shall I share my screen, or I will ask a general theoretical also?
Okay, 1 second. I'm allowed to sharing you. I'm making you as a host. 1 second. I think you can share.
Yeah.
Because I'm also not a host.
Can you see my screen?
Yes. Yes.
can we do find the components depending on push time and pop time? I calculated this problem. So the idea was I just want to clarify whether I'm correct. According to my calculation, at one point the stack got empty. Then we are adding the next vertex. So is that when stack
Yes.
is empty, that is a separate component. So should we go with that answer?
Yes, that is the correct
Is
way.
this correct? Okay, that's what I
Yeah.
want to confirm. Okay. Because in this problem, at one point the stack gets empty, then E and D was added.
When you are starting again, then that you are pushing again, then that
Oh.
means this is a second component.
So when the stack gets empty, the DFS is over, right? That's
Yes,
then
over.
separate component. Okay.
Yeah.
Yeah, that was my doubt. Thank you. Yeah.
Okay. Okay, any other query? Yeah, from mock, any other query? Yeah, my thank you.
Thank you, sir. Thank you very much. Yeah.
Okay.
Sir, how much similar questions from mock we can expect in quiz one?
So, how much similar question? The concept will be similar, but we cannot say that the exact question will remain the same. Okay, so concept we have. Today we have discussed sub questions. So concept will remain the same in quiz also, but exact question we cannot guarantee for any question.
Okay, the
Is there any material for?
Concept will not be beyond what we have discussed now.
Yes.
Is there any book to learn the recurrence relation? That I'm finding it very difficult. Recurrence relation.
Recurrence relation. So initially we are learning the basic recurrence relation for basic algorithm like quicksort and other merge sort like this. So in the big 8, we will also learn the way to calculate the complexity for different difficult type of recurrence relations.
Because
So
in our code it's fine, we are given, but sometimes there is no for loop. No, I think in one of the exam I forgot the steps were asked, but there were no loops. So in that case, it was very difficult. Even the time complexity, n steps they say.
So in BCAT, actually, sir, explain this recurrence tree approach, and based on that, sir, calculated 3 formula. If so, okay, just wait for the BCAT, and you will get the solution for recurrence
On my
based.
code it's fine, but apart from our code, it is very difficult. Even time complexity, sometimes they ask without even the loops, so by steps. That was very difficult. One of the questions I think in quiz I forgot, so that was very difficult to calculate. That's it. Okay.
Yeah. Okay. So any other query? So if you have any query from mock, you can also post on the discourse. So many questions I've already discussed on the discourse. You can go through that, and you can also post your query. Okay. Okay, fine. If you have no query, then we can wind up the session. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir.